Good afternoon. Good afternoon, evening, I should say. This is our last regular class before the final exam. Lots of thoughts go through my mind when I think about this time of the semester. I mean, I'm spending a lot of time in rehearsals and playing music right now, but I think about what was it like on the first day of class and how things moved along from there. I feel like things have gone, for me, pretty much the way I had hoped that they would go. And this last lecture I'm in, I feel like pretty much a sweet spot for getting it done. You've been turning in Project 2 already, so at least half of you have, so it fulfilled my expectations there. Hopefully, John, I didn't ask you in person, but was it enjoyable or a pleasant thing to be able to do a bunch of DSP stuff and tune in radio stations? Pardon me?
For the project?
Yeah.
I thought it was cool.
I mean, it's not stuff that you would have thought about. I pretty much promised in the beginning that the first project would be a lot more involved. It's going to take me a long time to grade it, and that's why it's not graded yet. But this one is supposed to be more of an application thing, and I'm allowing you to not have to thoroughly understand everything that you're doing. But I devoted about half last week's lecture to walking you through how it would work. So if you can believe me, and we're going to fill in some of the FFT details here tonight. So it's kind of a history of how I got interested in electrical engineering. I didn't really want to go to school. I wanted to fix radios and TVs, I think. I said, my parents, I have an older brother who had gone to college, and my parents were all set to pay my tuition to send me up to Michigan Tech or whatever school I wanted to go to. And I had been in an electronics program in my high school, special program that got advanced credits towards the community college electronics and whatever program it was, and that's what I was going to do. And they managed to change my mind. So, and all of you have your stories of how you've gotten to where you're at here right now. So we will go over and look at the FFT and the DFT to start off with, and then, well, I guess I should talk about the histograms that I put up. I was in a panic to get everything graded. I hit a major slowdown at one point this afternoon in grading, and then I was just running along really fast. So I do not have even the numbers, because I put that on a pad of paper and never got it. It's sitting next to my computer. So I can't even tell you exactly whose score is whose. I can guess, but here's the histograms, though. I took homework set number 6, and I haven't really entered that in, but this is what the exam looks like, pretty much, except for one person. Scores are high. It was almost going to be a 100 for at least one or two people, but then there were some things that I said, no, this isn't quite right, so I'm not gonna let you get 100. Not that I have anything against it. It's just being critical. This is the more important compared relative to the exam. So this is fresh, but you see sets 1 through 5. I could have added in set number 6, and it would have been a little bit more realistic. I have that data. I just was panicking, so I wanted to get this put together. So we have scores ranging from 80 up to 95 or something like that. So, and we have, more stuff to come. The project and the final exam contribute significantly. Homework, I don't expect that really to change very much because there's not many problems to be turned in, and all of you have turned in set number 7 already. I look forward to grading that. I don't want to hit any more major snags of confusion that slows me down, and 8 is very similar. 8 is probably even more straightforward or easier. There's less stuff to do there, but it's still all important stuff. So any comments about how I would take this if this was the final distribution? Or you got a specific question? Yeah.
4 as far as does that mean that we just take 4 classes?
Yeah. I have it set up in for these particular problems, I know how many points I'm going to give, and it's going to be the same number of points, for all the problems. So that way you can pick any 4.
I'm just curious where I'm at.
Yeah.
Why is the 69%? Can I ask you that, like the exam?
You want to talk about it? We can talk about it in a Slack call, and it'd be more confidential.
Okay.
I'd rather do that, or I could talk to you after class if you want to. If everyone else is gone, I don't want to take up class time though.
Okay.
To do that, and I don't want to do. You're entitled to confidentiality, so.
Okay. But like, if it is me, then I don't really care. Like, if they know about it.
Well, that doesn't really matter. It's just what matters is what you want to talk about specifically, because I have to defend why I did what I did, because what I saw wasn't what I was hoping. Yeah, it was not right.
Okay.
And other people made mistakes too. I didn't get the solutions put up because I was just picking and choosing, and getting this was a miracle onto itself. My wife decided to take a nap, and I said, I'll give you until 4:15, then I'm going to have to go, and I just barely got this out, but I don't have the solutions. A common error, though, on the exam was the scaling in the second to the last problem on the all-pass filter. There were little issues with that for some of you. Others of you got it totally correct. The thing about that second to the last problem, and I don't have it up on here, and I'm not connected to the internet right now. There were 2 scale factors. You got one scale factor from the requirement that the DC gain of the filter had to be unity. So that gave you one scale factor, right? 0.2305 or something like that, I think was the numerical value. And then there's another scale factor that's built into the converting it to a minimum phase system. So that comes out in front of the minimum phase system. And the all-pass filter, by definition, has unity gain. So that was a mistake that a couple of you made. Your all-pass filter did not have unity gain. It had a scale factor that was not correct. It should have been moved over. It's kind of like all numbers were in this row. There was first gain constant, the one from the all-pass creation, the minimum phase, and then the all-pass. So the common mistake was having something in the all-pass section that did not make it have unity gain, and then that made up for having the second gain constant. So what you had as an answer was correct in terms of all the way through, but it had to be, the all-pass section had to stand alone and have unity gain, so you couldn't slide that other gain. It was a factor of 4 is what it is. It was minus 2 e to the j pi over 4 times minus 2 e to the minus j pi over 4, and that product is 4 then. So that was the thing that messed things up a little bit. It's a really nitpicky thing, but I went through that in class, and then I posted an example after class that I thought made that really clear. So it's not a big deal. I mean, it's not like you don't learn. You learn from mistakes too, right? So I'm not really upset. I'm just, if I'm looking for stuff. And one person decided to change, and that was Miles. He decided to change the problem with the equalizer problem to a totally different filter, which made it really easy. But I don't know what happened there, disconnect, which we can talk about individually. That threw me for a loop too, because I'm like, wait a minute, this isn't even the problem. It's a different problem. You ever had a professor say, if you change the problem because it's a problem you can work and not the problem, you can't work the one that I gave you, is that supposed to be acceptable? I don't think so.
Which problem is that?
Problem number 2. Yeah. Yeah. I'm going to get going, though, because we do have plenty to do, and I've got extra stuff I can talk about. Yeah. I'm going to talk about this chapter, which we won't go through, and I'd also like to briefly look at the digital filter design chapter, too, if we get a chance. Meanwhile, back over here. And you've probably seen the FFT before in 3205, but I'm hopefully going to give you a little bit more thorough introduction to it all the way through. So the first thing that we're going to do, and we're not going to be able to cover everything that's in the notes here, is we're going to look at what the DFT is all about. And the FFT is an efficient DFT algorithm is what it comes down to. So the second half of tonight's lecture will delve into the FFT itself and how it was discovered a little bit. It's a very interesting history thing too. It's not just something that has always been with us, but it was discovered before the turn of the last century. That's the really interesting thing. It was discovered by somebody that didn't even have a computer. They just came up with the algorithm, and it was originally thought to have been discovered in 1963, I think, but then research and papers published and things found that somebody had actually stumbled into it and created the algorithm back around 1898 or something like that. You know, those things do happen, though, right? People are onto something, and then they never had the computer to actually do it, but they found something that they could do. So why did I learn about this? It's because I was at the International Signal Processing Conference in San Francisco that year, and there was a special session because it was the 30th or something anniversary of the FFT being discovered, and then it explained to us that really it was discovered for applications with computers, but it was actually predated by something else that was, not totally on track.
For homework 8, where you say 4 problems required, are the other 2, would they be extra credit? Or would
they can be extra credit if you want them to be. But I will decide what I want to do with them when I grade them, but I think I said that in the sheet, don't I?
Yeah, you just say 4 required.
Yeah, so that means you can work them for bonus if you want to. And if they're all hacked up and work poorly and you get only a few points, that's fine too, because you'll get what I think you're entitled to get as a bonus. But they're all hold the same number of points. Okay, so getting into this, sampling the Fourier transform. There's different ways of angling into this, and the book kind of looks at 2 different approaches. I like this approach here because it's more natural for where we're coming from, and we don't have a lot of time. We could go off and discuss Fourier series for discrete time signals, and we'll see that we get that in the end anyway, but this way seems pretty natural to me. So we start out with a finite duration sequence of n points total, as shown here, and then we look at taking the DTFT of that, so that's what this is, of course. Which means it's evaluated for all values of omega, and it's periodic with period 2 pi, all well and fine. So we can evaluate it at any precision of omega we want, and it just repeats every 2 pi radians. But now we consider sampling the DTFT at points that are taken based on the length of the sequence. So 2 pi k over n, where k runs from 0 up to n minus 1. So we're going to have n total points sampling of a DTFT of an n-point sequence. So that ends up looking like this. It'll be called x of k in the DTFT notation. It's really just the DTFT sampled or evaluated at these omega sub k values that are spaced uniformly along the axes between 0 and 2 pi, but not going all the way out to 2 pi, because that would start over again with the same value. And then this notation gets introduced, this capital W sub n to the kn, and this will be used in the FFT definition as well, but it's just saying that it represents e to the minus j 2 pi over n. And this is sometimes called a twiddle factor in an FFT. It'd be something that would be in a lookup table or of some sort or another in a computer algorithm. But it might not, this is the base, and then you might store all of these values, because these would correspond to, as k steps around, would correspond to the values taken around on the unit circle, right? Evaluating e to the minus j, e to the minus j k over n as k goes from 0 to n minus 1. So this is what then those sample values look like, and we're adopting the notation now that we're going to not think of it as omega, we're going to think of it as being an index of a DFT point, and that index corresponds to sample values, discrete values taken from the omega axes. And if we take this further, because we've studied the z-domain so much, we could also view this as taking the DTFT and sampling uniformly around in the z-plane on the unit circle. Is that good? There might be one of the homework problems that kind of has that. You have to take that view to think about it if you choose to work that homework problem. So this forms the DTFT, the forward transform, which we were just looking at. So this is the forward. And then, and we're going to have the proof of this, the inverse DTFT or IDFT. One is called the analysis, the other one's called the synthesis. And if you want to think about what that means, it's more along the lines of the way a Fourier series gets developed, but it's saying we have an endpoint sequence and we want to analyze it to see what its harmonic or frequency contents are. So we have an analysis of an endpoint sequence into n frequency bin values. Does that sound reasonable? Rather than seeing a continuous spectrum, we're just going to have how it lumps itself out when we sample it at those endpoints. The inverse DFT is a very similar algorithm. It has a negative sign on this capital W, or the e to the j term, j pi over 2 pi over n. And then it also has a scale factor, 1 over n out here. And that's to make the amplitude value come out scaled. The proof of all this, and this is very concrete proof, there's no hand waving of interchanging orders of sum and integration or anything like that, because we have two finite sums. We can interchange the orders of the sums. So we take the inverse DFT equation and plug the forward transform inside of it, just plug that in place of x of k, and then move the sum on m to the outside, move the sum on k to the inside, and what we're left with is this expression, and the brace there says that that evaluates like a Kronecker delta function that you may have seen in Fourier series or maybe physics or somewhere or another. It's a function that's zero everywhere. It takes on, for discrete arguments, it takes on values of 0 everywhere except when the argument is 0. So it acts like a delta sequence, actually. And you can evaluate that, because if you try to evaluate this summation using what? Just as a quick review, because we started here a long, long time ago, I went from here to here, and what allows you to do that? Just to pardon me? Yeah, the finite geometric series. So see, even to the last day of class, we're still leveraging off of that. So plug that in, and then you go to evaluate it, and you get worried about, singularities, if the numerator and denominator are 0, but you can use L'Hopital's rule if you want to consider m approaching n. But then whenever m does not equal n, we're going to get 1 minus 1. Because we have an integer value in here, and e to the minus j 2 pi times an integer is going to evaluate to 1, and then the minus sign. But when it's 0, we have 0 over 0, but we can take the limit as m goes to n, and then we'll get n. So that's how that gets developed. And that, when that gets plugged in up here, the 1 over n cancels out, and then it sifts out x of m as x of n from the Kronecker delta function. So this establishes that we do have a forward and inverse transform called the DFT, and the true wonder of the DFT, now that it's been revealed, is what can we use it for? Because what's super cool about it is all of this is numerical calculations. There's no choosing, how fine steps to take for the evaluation of omega. You just crank it out, and it cranks out very efficiently. So we just do it, and it's numerical, going both from time to frequency and coming back from frequency to time. So it's very, very, very nice. And your project relies on it heavily because, remember last week, it uses transform-based filtering using DFTs, or actually FFTs. But now we can relate it to a Fourier series concept, in that we have a finite length signal expanded in a Fourier series is really what we've done by the synthesis and analysis discussion. So we actually have a DFS, and if you were thinking about Fourier series from way back in 2610, the very first signals and systems class, whenever you wanted to find the Fourier series for a periodic signal, you always took out one period of the signal and then worked with that with the Fourier integral and got the Fourier coefficients, remember? And then you automatically are assuming that you have that one period. All those periods just run up and down the time axes. That's exactly the way we can interpret the way the DFT works here. The DFT is blind to the fact that we don't have a signal outside of the interval 0 to n minus 1. It just assumes that it's there, just like a Fourier series expansion would. You're working on one period, n points long. So the book also talks about something called the periodic extension. So they will use the tilde over the top to mean that we're talking about not the finite sequence, but the sequence with its periodic extensions. And because we're talking about capital X of n as being the forward DFT, and it already was periodic as a DTFT, samples of the DTFT are going to have a periodic extension as well. So that same idea remains. The interesting thing that I think about, because I get confused on this myself, I remember being on somebody's, I think it was a dissertation, maybe it was a master's thesis, a control systems dissertation, that before Dr. Plett and Dr. Trimboli were here, it was somebody else that was in the controls area here. It was somebody from a company. Colorado Springs had a history of being involved with companies that made disk drives, and disk drives were floppy disks, regular magnetic surface, hard disk drives and everything. So in that business, the platter of the disk drive rotates around once, and then it repeats again. So there was something really interesting, and I don't remember the details, but this person was doing something with the DFT in his thesis that took advantage of the periodicity. So in that case, because the disk was spinning around, it's repeating itself, but the head that reads off the disk would get a different signal if it moved to a different position radially as it spun around. But it leveraged ideas from the DFT. I just thought it was interesting. Well, given that we've just talked about the forward and inverse transforms, you can actually take and form a matrix equation. So we can take samples, our sampled signal, n points long, can be put in a column vector. The DFT points can be put in a column vector. And then we can form a matrix of these W weights of different powers. And this is how that matrix would be set up, so that when you multiply the matrix pre-multiply it times the column vector of time domain samples, you get the frequency domain samples. And then knowing that the inverse of this matrix times x of n, in other words, just multiplying both sides by the inverse of w, we would wipe it out on the right side, and then we put it in on the left side, right? So we'd have a way of saying w inverse times x would give us x of n, so we have this equation. But then this establishes a relationship between what it would be like if we use the true inverse discrete time Fourier transform, which would be this matrix, the conjugate, and 1 over n. So that tells us we have what's called an orthogonal matrix, which maybe is something was mentioned in linear algebra when you took that a long time ago. Remember orthogonal matrices and things, you know, various other things that came along in that class.
I try to block that class from my mind.
Really? But it's, matrix theory comes up in a lot of interesting ways. Control systems, most certainly, and state space modeling in control systems. What I was going to say, though, or what I will say right now before we move on to start looking at the some properties of the DFT, this modeling or this representation of the FFT or the DFT in inverse DFT led to a branch of efficient algorithms by viewing things as a matrix decomposition and being able to simplify the number of steps involved. We will be looking at the radix 2 algorithm, which was discovered by a different set of steps, but there were other algorithms that were studied, that were developed, that grew out of this matrix point of view. I got involved with it on a really early consulting project for a company, and I just had to look at certain things. It's very fuzzy in my head, but I just remember learning more about the matrix point of view. Okay, so now we're going to take an example, and we're going to have some eye-opening exposure to what the DFT can do and how we can mold it to do something very, some very useful things. So we start off with just a pulse, a rectangular pulse, endpoints long. So we're going to consider an endpoint DFT where the signal has L points that are 1 and n minus L that are 0. So first off, if we assume that n is greater than L, because that's what's going to, greater than or equal to L, it's going to have this make sense. We're going to have some points that are 1 and then some points that are 0, and that defines the endpoint sequence. We can take the DFT of this sequence, and we did this a long time ago. This was our rectangular pulse. We took the DTFT of it, and we got this sine x over x, or sine nx, sine lx, I guess, over sine x, kind of a function that has the, remember I later called this the alias sinc function. The sinc function would be sine x over x. The alias sinc function was this part right in here. Aliasing as in you put up multiple sinc functions separated by a scale factor and repeating every 2 pi, then the tails of them intertwine, and then it forms this function. In MATLAB, for example, they call it the Dirac function, D-I-R-C. Python doesn't have a name for it, but it might be in, well, you can create it using the sinc function. You can create it in Python, but I know MATLAB has its own name for this function. At any rate, there's magnitude and phase. So now we go in and take the DTFT of this pulse train-like signal. In this case, I'm going to do an example where it has 10 ones, and then the rest of the samples are all zeros. So the first thing I'm going to do is I'm going to set n equal to L so that the filled black stems there are our endpoint sequence. 0 to 9 makes 10 points in total, and then the open stems to the left and to the right are the periodic extension. So, and this is important to be able to visualize why the DFT does what it does when it operates on this signal. We're going to take one period of this constant signal, if you look at it that way, and we're going to find out that the DFT just says, well, I'm going to get 1 at 0, and then I'm going to get 0 everywhere else, and then when I repeat, I'll just get 1 back again. And if you think about just a simple spectrum idea, this is actually what you would expect. If I'm just putting a DC signal into a transform, a Fourier transform, I should get all the energy of the spectrum at DC. There's no variation in it, and everything else is 0. And you can trust that thinking more when you consider the periodic extensions. Just extend the 10 black stems with the white stems that run up and down the axes. So the DFT is just working with its blinders on. It looks at the 10 samples and it says, I don't see any evidence that this thing is moving around. It's staying steady, and I get a spectrum that corresponds to that. It's totally acceptable to have that happen. But in reality, we know if we take the DTFT of that pulse train, where we have the context of the entire time axis, we see a spectrum that looks like this. So that's why in this picture down here, I showed in dashed or dotted line what the spectrum expected is for the pulse train. But because the DFT is blind to the bigger picture, it thinks automatically that we extend it with a periodic extension, and the DFT just does only what it can do. But now we're going to try something else. We're going to append some zeros. So we're going to append n minus L zeros to see what that will do. That will increase the number of points to 20. In this case, I'm going to have n is equal to 20. So that means I will get the set of DFT points will now double, and I'll actually start getting sample values of the true DTFT just by padding the sequence with zeros. Does that make sense? We're giving it more information. Again, we're giving it this thing right here. This looks really like one period of a square wave, if you want to think of it that way. And what would one period of a square wave have for harmonics? It would have first, doesn't have the second harmonic, but it would then have the third harmonic, so on and so forth. Things you learned in 2610 about symmetrical square waves having only odd harmonics. And there's, obviously, if you look at this picture now, there is also still a DC component, because the average value of that is half the time it's on, the other half the time it's off. So that would be this value right here. What the DFT forces you to do is start thinking differently about what it, how it operates. It's extremely useful, though, because of its numerical implementation aspects. So here I just bumped it up, and I'm going to switch over to what I have in Python right now. And this is what I pushed up late last night. This is why I wasn't grading, because I said, no, I need to push this out the door and refine what I had up there earlier on the website. That's how come I got so excited last night, because I wanted to pull down the old version of this notebook, and I couldn't find it. I mean, I couldn't download it because the web server wasn't working. And then I got really excited about that and spun my wheels on that for a while. But at any rate, in here, I'm just doing our standard import. And the first thing I do in here is I just, because of the way I know NumPy is set up, NumPy has the FFT as a sub-package of NumPy. So if I'm importing all of NumPy, I will get the top level FFT, but now if I press tab when I'm sitting in here, I'm going to see that here's what the sub-module is, or sub-package within NumPy for FFT. So I have FFT, this is a two-dimensional FFT some other variations. I don't actually know what all of these are because I don't typically look at them, but we're primarily interested in just the one-dimensional FFT, and which is FFT, and then IFFT, this one right here. So, I mean, if I was to put in, for example, hit tab there, just prove that it is a two-dimensional FFT, I can go shift-tab over that, and it tells me computes the n-dimensional discrete Fourier transform on any axis of an m-dimensional array. So actually you can extend this. I've not even thought about that. I've done some image processing, which would be 2D stuff, but so that's what you do there. For us, though, we're just going to focus on being able to use the 1D FFT, and then if I put the I in here, we'll have inverse one-dimensional FFT. And some of the features of this, which I won't go into explaining this as much as just saying what I know works, is that I put a value in for X or A, and then if I don't put any second argument in, it will just compute an FFT or DFT of that length sequence. If it's a 10-point sequence, it will be a 10-point transform. But the second argument, you can set what the length of the sequence is. So if I was to put the second argument as 10, it will just do the same thing. But if I make it be 5, it will truncate that sequence to be just the first 5 points. If I put 20 in there, it will zero pad the 10-point sequence out to 20 total points. And if you're remembering back to MATLAB, if you ever used it in MATLAB, it's the same way that it worked in MATLAB. You can truncate or pad if you use the second argument. So that's exactly what I'm going to do right here. I'm going to create a sequence of 10 ones, just like the example in the notes. And just to kind of lay this off to the side for right now, I'm going to do a time it on this. And I'm going to pad my 10-point sequence up to 1,000 because I'm going to put NFFT inside of here. And I ran this morning on this computer, but now that I'm running the video and everything, it's actually working pretty poorly. These two numbers were identical, even though one is a power of 2 and the other one's not. But now when I just ran it, I got more than twice as long, which to me makes sense because my computer is processing the video, streaming the recording I'm doing. I did this, though, to kind of dramatize how the modern FFT algorithm families are pretty efficient. That's just not that much faster. And we could try 1023. Now it got worse. Notice 1023 was worse than 1000. And yeah, we already ran this one. So this is just showing you that there is efficiency to be gained. This computer is very old. On my new MacBook with the M4 processor in it, the Apple M4 processor, it's a few microseconds, I think. It's much faster. And, you know, as they always say, your mileage will vary, so you can try it on your own computer and get an idea of how good your computer is in terms of speed. All of these algorithms that are used in NumPy, though, come from FFTW, which is a library that was created down in Texas. The fastest Fourier transform in the West is what it stands for. So it sounds like Texas, doesn't it? FFTW. Amongst engineers, I mean, you can get versions of it to work with in C libraries and other things. It's open source, but it has some caveats on it. I just don't know the details right now off the top of my head. But now we'll get into the zero padding. So here I've got the exact problem we were just looking at in the notes, and I'm going to zero pad. I'm going to make the FFT length 80 when I have only 10 points. And you can see it's filling in tighter and tighter, and something like what we might have been doing earlier in the semester using freq z, it actually would be better at this point to just do this with plot. And this is how freq z, which we've used earlier all throughout the semester, actually does its calculations. It's using an FFT under the hood. It'll take the numerator vector, FFT it, takes the denominator vector and FFT it, and then it divides point by point to get the freq z result. Is that believable at this point? So any more thoughts on that before we just move on? This is the basic stuff, but it just shows you how powerful the FFT is, though. We've been using it all along. We have not been avoiding it. It's been used everywhere, unless you chose to write your own algorithm to do the frequency response, which you can, but it's there to help us out. So what about the IDFT? It's just as fast, except it has that extra scale factor in it. The conjugation doesn't change anything, but you do have to scale by 1 over n. So we'll talk about that a little bit later. But what I'm doing here is I'm just showing that in this example, I'm going to FFT 1, 2, 3, 4, 5. So here's the values, what we get. And we're going to be looking at symmetry here in a second, but I stayed in here a little bit longer. So now I'm going to inverse FFT those 5 points. And I get, with some numerical precision, I guess if I was to drill into it, I get back, when rounded, 1, 2, 3, 4, 5. If I was to take the real operator off of here, at this point in the standard format of NumPy, it's not showing me any tiny, tiny little numbers here for the imaginary part, but actually I know they're there because that's just the nature of doing finite precision, double precision floating point. There will be some issues like that. We're going to be looking at symmetry here in a second, and I think this is another example. It's in the notes. So here I just take 1, 1, 2, 2, and those are the 4 DFT points, and I'll get back, of course, 1, 1, 2, 2, but we'll be discussing symmetry for real sequences. So this is the DC spectral component. This is, as long as the waveform is real, the DC spectral part is going to be real also. So it's 6, but then this point is a quarter way along. No, pi over 2. This is the sample at pi over 2. This is the sample at pi. And then this is the sample at 3 pi over 2. The second point and the last point are conjugate symmetric with respect to each other. Just like in the DTFT, the frequency response magnitude will be unique only on 0 to pi. The phase response will be just flipped on the interval from pi to 2 pi, and that's why we're seeing the conjugate stuff going on here. We'll go look at that, the math of that, and then we'll eventually get back over onto this again after we do circular shift and other such things. So the first thing is this little section, which I call like the anthology of Fourier transforms in your lifetime so far. You started learning about continuous time Fourier representations. Fourier transform was thrown in there. I guess at UCCS you start with Fourier series first, but these are the 2 continuous time Fourier-like transforms that you've been acquainted with so far. This semester we got into the discrete time Fourier transform, DTFT, periodic or non-periodic sequence. We go back and compute the Fourier DTFT sum, and we get a continuous spectrum that repeats every 2 pi. We come back through the integral to get to the sequence domain again. Then what we just have been looking at here is the DFT, but then we managed to realize that we actually have formed the line spectra for a periodic sequence. In the process of doing this, we're doing a Fourier decomposition into Fourier series, and they're both identical from the mathematics or the pictures I have plotted here, but they have a different interpretation because one is a series representation idea, and the other one's thinking of it as samples of the DTFT, but they're equivalent. They end up being the same. So it's just some added thought process can go on in here. I'm fine myself with just thinking like this. This is just like a stepping stone, and I skipped that. That's what I skipped. The book in this chapter starts with, I think, the Fourier series, and then quickly gets to this. And for expediency, I just didn't want to belabor it. Over all my years of teaching linear systems, like 2610, I never really found that people enjoyed Fourier series a whole lot. As a matter of fact, when I wrote the Dummies book, my editor said, "You're going to have a chapter on Fourier series?" And I said, "Yeah, I think it's really important because it's so valuable in communications theory, having harmonic stuff." And they said, "Well, we didn't think you would need one in this book because we were under the impression that it's not that important anymore." And Dr. Zemer was still here teaching when I was writing the book, and he said, "It needs to be in there," is what he said. So it is in the book, but I'm just giving you an idea that they were thinking that it was no longer that important to electrical engineers. And I'm saying that because what do you think now? Is it kind of not been as important? Okay. You said what, John? Yeah. Well, there's another side of it too that comes in fields and waves and solving partial differential equations, boundary value problems where you do a Fourier series expansion to solve for some electric field or magnetic field in a structure. And it's not based on the harmonics as much as it is on the geometry that controls it, the Fourier representation. And I took that when I was still a senior. I'm pretty sure. Maybe I took it as a graduate student. Okay, DFT properties. So first one, linearity. It holds just like the DTFT, Z transform, and so on. So we can take a linear combination. The only caveat would be that if these sequences are of different lengths, N1 and N2, we have to come up with a common length in order to be able to talk about a transform that works with N points. So you would either truncate one to match the other one, or you would zero pad, or zero pad them both, because we're going to see that zero padding is important a little bit further down the path from here. So it's just a superposition then of the two DTFTs, where we're implying that the DFT length is N, which say me, I guess my way of thinking of it is make it the maximum of N1 and N2, or take it up to the next higher power of 2 for an efficient implementation with a radix 2 kind of algorithm. Okay, circular sequence shift. This is a new property that doesn't exist in the aperiodic, DTFT domain, where we don't think in terms of periodic extensions and so on. So we have to think this way. So we have to think that when we have a time shift, we're multiplying in the frequency domain by e to the minus j omega m. That's the delay theorem, right? We delay a sequence and we get a phase shift, a linear phase that gets applied to the spectrum. So now how does this work out in the DFT domain? So we have x of n and capital X of k are related through the DFT I DFT. Suppose we have x1 of n being W sub n of mk times x of k. What does that make x1? So if we write that out and go ahead and compute, we're taking this as our input to the IDFT, and this is our complex weighting function. When we do that, we see this argument appears when we put everything with a common W sub n, and that would be interpreted immediately based on our understanding of the inverse DFT that the new variable, the time axis variable, is not going to be n anymore. It's going to be n minus m, but it's going to be n minus m with this subscript n, meaning that it's modulo n. So we shift it back and forth, but it will repeat because we're actually shifting in the sequence domain a periodic extended signal. And we just put blinders on it to see it in that interval 0 to n minus 1. So this is the example that I did here. And this is the type of example that could appear on an exam one way or the other. I give you this, and I ask you to tell me what the shifting factor is, the complex factor, or draw the picture in the sequence domain of what this factor would give. So here, the factor is m is equal to 3. So the entire sequence, a plus 3 means it's going to shift to the right by 3. And that's what's going on right here. It's shifted over by 3. And then these points here are shifting into the periodic extension domain, but actually they're rolling around and show up over here. And Python has this function called roll that I'll show you here in a second. It does exactly that. It will take n points, and then if you shift it to roll it right, it takes the values at the end and rolls them on the front. Shift it left, they roll off the front and come onto the end. And I use that function actually in the filter bank too, for rolling FFT points or DFT points. But here, it does exactly that. So circular shift by 3. This is the way one book had it explained. It was like looking at things in a circle and thinking of having click stops on this knob, and the points that you can stop at are the points in the DFT. So you click it, and the points rotate around circularly in a circle. So that's the theorem then, or the property, circular shift. Here's my Python example. It's the one that's already running in the notebook, so I'll just show it over here. So I create an a to the n type sequence, decaying off, but I used the discrete rectangle function here to truncate it. Truncate it at 10 points, or actually 9. So it goes 0 to 9. And then over here, what I'm going to do is multiply the sequence in the frequency domain by this factor here, e to the minus j 2 pi 16k times 12, or 2 pi over 16 times k times 12. So the W sub n has got the minus sign built into it, right? You have to go back. We want to make sure. Should I go back? Make sure you remember that it's automatically got it built into it. Let's go look at that again. Because it goes with the def and the DFT. So the DFT has, way back over here, it has the minus sign built into it. So it's W sub n on the forward transform, and it's W sub n to the minus whatever on the inverse transform, which gives you the positive. So if it seems confusing, sorry. This was to make sense for the definition of the DFT. So let's go back over here. Get the right position to get started again. So I multiplied by 12 in this case. So I shifted the sequence all the way to the right by 12, and it wrapped all the way around like this. Try another number, just for the fun of it. I have 12 in here right now. You're saying it didn't change. That's because I rolled it to the left, and I rolled it to the left by 4. So it's the same thing. Are you okay with that? I mean, I'll put in something else maybe that just do 4. So I didn't explain here, but here I'm plotting it twice because one time I'm plotting it using roll. Here I'm just plotting the sequence, and I didn't change that, so that needed to be changed to 4. So now they're the same. So the roll function is emulating what in the DFT domain the complex phase shift is doing.
And this would be a right shift, right?
Mm-hmm.
Which corresponds to like n minus 4.
Yeah, exactly. So when I used roll here, I was putting in roll x by 4, and if you look at roll definition, roll elements along a given axis, and it's a positive axis. So plus 4 means rolling it to the right by 4. I used roll when I was solving the first project problem too, because I wanted to take the filter's history and delay it. In other words, I wanted to put get rid of the old sample, the oldest sample, so I rolled it to the right by 1, and then when I came along and had the new value calculated, I put it at the beginning to form the new state vector for computing the output. So that's where I've used roll before. It's not friendly that roll actually wraps that old value around, but if you set your code up properly, you can just roll and then quickly write over the value that rolled off the end and came back again. You'd like to have a shift left or right where you just are putting a 0 in, and I think Julia has both. I'm not positive, but I don't think Python does. There's something in one of the languages where you have a shift and a roll both, but I just remember roll, so I usually end up using it more often because it's something I remember. Duality is just simply saying, just like with a Fourier transform in general, you can take and redefine the terminology of the transform and look at it turned around. So here we take the DFT of the DFT points with n replacing k, and we get out of that n times the original sequence time reversed. So it's just showing you what the duality property would be like in a DFT, which says this. It says if we take in DFT a second time, it gets us back to the sequence domain, but it puts a scale factor of n on, and it is reversed. Symmetry properties, there's a bunch of them, just like we had for the DTFT. I really only want to emphasize this last one, which is a standard one. If x of n is real, if we conjugate the entire DTFT, we end up getting the conjugate of the DFT points, but at n minus k. So it's just showing that it's conjugate symmetric. From end to end of the DFT, the points are conjugate symmetric, or the magnitudes are even and the phases are odd. And this is a property you've seen before, so it's not a new thing. And if you are fuzzy about this, just remember the DFT is just a sampled version of the DTFT. So you can always say, I know it worked there, it has to work here because it's the same, doing the same thing, except we're just sampling it uniformly. Okay, so this one is a big application area, grows out of circular convolution. It's not that we want to make things circular and make our lives more complex by having, I'm going to make this sound silly, but by going in circles, we don't want to get twisted up, and that's another pun, unintended, but the reason why we want to consider this is, it was really cool way back in the beginning of Signals and Systems when you said, oh, I could avoid that ugly convolution, integral or sum, if I just went to the transform domain, either Z domain or frequency domain, multiply, and then come back again. But the coming back is hard to do in the discrete time domain because it's an integral. But now that we have a DFT, which is a number crunching thing, we can go to the frequency domain and come back with another number crunching operation, and let's learn how we can do it. Circular convolution introduces time domain aliasing, but we're going to learn how we can avoid that. So here's the basic statement. It says we want to consider the product of two DFTs to form a third one. We're expecting that what we're going to get is a convolution of two sequences, the standard convolution sum that we've seen before, but instead of using x1 and x2, we'll be using the periodic extensions, because we know that already with the DFT we can't escape the periodic extensions. They're a nemesis in a way, but if we want to be able to take advantage of the DFT powerful calculation capabilities, we have to learn to live with these periodic extensions, and we can overcome that. So we can investigate that by just working through the math here, which is what I did here, just to say the ESX3 would be the circular convolution of two endpoint periodic sequences. And the book likes to put a circle around the asterisk for convolution and then put a subscript n. I think I'm probably inconsistent in these notes because it takes more typesetting language stuff to get the circle around that, but it's not possible. I mean, it is possible. These notes were done with LaTeX. I'm pretty sure Typest, which I was going to give an award today for the person that got most into Typest, and that was definitely Lake. He went in over his head with it, but you did it because you were interested, right?
Yeah. I mean, I'm still using it for all my other reports now.
You are? Has anybody asked you what you were using?
No, they just sat there looking like, cool, good job, and move on. But then I like it, I appreciate it.
Yeah.
It makes my reports
Okay. So you got another benefit out of being in a class with me. You latched onto it. That's such is the life of an engineer. You get fascinated by something, and then you hook onto it, and then you see where it takes you. I haven't showed it to anybody at where I've been working at ARCA, but I definitely used it because I had to do it. And I had to make a report that was more readable, and I wanted to get it out of my Jupyter notebook in a way. And what I did was I exported it out of the Jupyter notebook as a markdown file, and then Typest will take markdown documents that have graphics and everything saved from the export from Jupyter Lab, and it will take the markdown and convert it to a Typest document, and then you just simply take all the SVG graphics, paste them into your folder, and then have to wire them up, so to speak, but then you've got them, and it does a pretty good job of converting markdown. And the markdown could have your LaTeX markdown math in it, and it will convert that properly too. So that's pretty cool because Typest is the new kid on the block, so they have to play well with LaTeX people, which I grew up learning that, but pretty exciting. Okay, the project solutions that I wrote for the project 2 were written by me in types, and I did exactly that. I converted it to Markdown and then exported it and imported it into types. That was a year ago, that was when I was first starting to play with it, and I was trying different things out. So this notation for circular convolution. So let's come back from our break, and we'll do this. We have a little bit more to go, and then we'll be switching over to the FFT part of it. So let's come back. Between 5 and 10 after would be good by me. Okay, we're now going to look at an example of just circular convolution. So it's possible that I could ask you to do a circular convolution on the final. These types of problems can show up. And what I mean by that is, since you're not going to have a computer, doing it with a two forward DFTs and multiplication, which is what I do beneath this, could actually be more complicated than just knowing what's involved with circular convolution. So this is just a simple 4-point circular convolution. In order to do x1 convolved with x2, what do you have to do with any convolution is you have to take and flip one sequence and slide it, and then multiply them together. So here I take x1 of m, and this is going to be x2 of n minus m, and m is the variable that we sum over. So we put everything from the equation we were just looking at, we put everything in terms of m to sum over just where the blinders are. The lack of blinders were free on this interval, 0, 1, 2, and 3 for a 4-point sequence. So that's the one sequence. The second sequence is x2 of 0 minus m. So all I'm doing is taking the x2 there, spinning it around so that it's pointing down in this direction. Does that make sense? It's spun around and it's pointed down here. But because of periodic extensions, I just get it filled in based on knowing that it's because it's flipped over, that the periodic extensions that line the interval 0 to 3 are these 4 values. So then I just do 2 times 1, 0 times 2, 0 times 1, and then I get 1 times 1, so I get 3. See how that, it's just doing the convolution point by point, multiply and add. So do that for all 4 cases. There's 4 cases to do, and then because of the periodic extension nature of everything, it starts all over again. So those are the 4 points. No one would do this in their right mind, because that's why we're studying circular convolution. How would we do it in the transform domain? So in the transform domain, and I could ask you this question too, I suppose. I mean, I haven't looked at any old exam problems recently. I could say, okay, it's a 4-point transform, it's not that hard. You could write out what x1 of k is, and then you would just evaluate it. This would be the DFT at the 4 points. We're talking for the 4 points, and then evaluating it at k is equal to 0, 1, 2, and 3. And those are these 4 values here. And do that for x2, which was 1, what is it up here? 1, 1, 0, 0, whereas 1 was 2, 2, 1, 1. So get the 4 points for x2, the 4 points for x1, and then I just brute force multiply them together, form the product, get these 4 points, and then inverse transform. Using the inverse transform definition, the 1/4 out in front, we have 3 terms that are active. The x3 of 2 term is 0, so it doesn't enter in, but these are the 3 terms, and then we just have to plug in the values of n as we range from 0 up to 3, and we get 3, 4, 3, 2. And this matches the hand calculation, 3, 4, 3, 2. And unfortunately on the exam, you can't go into Python like I did here, but you can certainly do some practicing if you want to, and you can certainly do that in the homework that you're going to do the transform. So here I just I just wrap it all up, 2 forward transforms, the product point by point, and then inverse transform. And then, because there might be some numerical issue with small, tiny, complex values, I just throw away the imaginary part and keep the real part. So 3, 4, 3, 2. And of course, that would just keep repeating if you wanted to do that. And I've got that in the Python down here, but I'm not going to really mess with that at this time. It's too trivial. We're going to next look at example 7.4. My watch is now connected to my phone, and I just got your message. No, it's good. I mean, I'm actually running again on my phone. I just can't get this laptop to work. So now we need to talk about time aliasing in circular convolution. What we just did with circular convolution is just an exercise to prove that you can convolve in the frequency domain and you get a sequence back. 2 forward transforms, 1 inverse transform. And right now you're thinking, no, that's just so much work. It's not. With the FFT efficiency, we'll see towards the end of class here, it's worth it. I think the numbers, you have to get up into FFT lengths that are 64 or 128 or somewhere in that region. It becomes more efficient to do filtering in the frequency domain, as long as you have the infrastructure to instantiate your transforms. So now we're going to look at, really get motivated about doing convolutions in the frequency domain. So the first thing is to look at just convolving 2 finite point sequences. We did this a long time ago. Remember, the rule of thumb or the formula is if you have an L point sequence and a P point sequence, you're going to get at most as a result of convolving L plus P minus 1. I suspect most of you have memorized that, or you just know that's what's going to happen. So linear convolution of an L point and a P point takes L plus P minus 1 points total. So how can we make the circular convolution obey this, act like linear convolution? We know we can zero pad, and that's exactly what it is. We can zero pad x1 and x2 up to a large enough number. To actually do the convolution, we have to at least do the max of L and P, but if we take it up to an even higher number, then we can get a clear result without any time aliasing. And this is a concept I came up with years ago, saying I'm going to draw this out in pictures and then try to make you understand it in pictures why it's broken without zero padding. So normally we think of convolving x1 with, say, x2, so I've got it flipped over right here and it's going to slide through. So the clear one is like what the linear convolution would do, but when we have circular convolution, we have all these other gray periodicity things in there, and those are like our interference or jamming waveforms. They're just messing our life up for us. So we can see that that is what the circular convolution brings in. It brings in the time aliasing, and if you write it out, you can write it out as getting a periodic signal, but it's not going to be the one we'd expect from linear convolution. And so I took it upon myself, like I said years ago, to try to visualize it graphically. So we have the different periodic extensions. If we go ahead and convolve with the signal and its other signal, we're going to get with the time shifts, say these are the neighborhood convolutions we get from the gray signals convolving with the original signal. And we're wanting to keep what's in this interval 0 to n minus 1 to be just the linear convolution. So we look at this and we see that we'd like to get, this is what we want, and we can say it really comes down to that's something that we don't want. So as we drop down, all these terms are going to sum up into here. So what are we going to do to make sure that we don't get this r is equal to 1 term interfering with the r is equal to 0 term. That's talked about, I guess, in the end of this. What did I write that out? Yeah, it's right here. So the only term that really is a threat to us is the r is equal to 1 term out of this infinite number of terms, because we're really only wanting to evaluate. The key is we only care about what's on the interval 0 to n minus 1. So in order to make that work, we can choose to introduce 0 padding on x1 and x2 both. So x1 was p points, x2, or x1 was L points, x2 was P points. We'll put in a certain amount of 0 padding, enough to make sure that this r is equal to 1 term will end up with all zeros in that interval. Does this grab you in any way to say that I have something to hold on to? I can pad it, and then I could see that the r is equal to 1 term was the one that was bad, and we'll just pad it with enough zeros so that we don't have any time domain aliasing. So the formula is going to be, we're going to choose L, or N I mean, to be greater than L plus P minus 1. So we're going to purposefully not just make N the max of L and P, we're actually going to build it up to be long enough to not allow any time aliasing. So first example I took in here was a couple of 6-point sequences, and if you just convolve the 6-point sequence with itself, you get a triangle. And if you now put that in the context of our convolution, circular convolution ideas, we get this is what we want from the linear convolution, but then we get this other term. This is like the r is equal to 1 term, and it sums in, and we get it's all cluttered up. This is like frequency domain aliasing, where we hear one tone on top of the other because they all collide. This is in the time domain, samples from this piece right in here combined with the linear r is equal to 0 term and loaded it up with junk. So we start by padding it. So we choose n greater than L plus P minus 1, or in this case 11, greater than or equal to 11. And as soon as we do that, we see that this n is equal to 1 term is totally clear. And of course we're clear here already, but we padded, so now we get what we want. So in the context of homework and exam questions, it's not going to be the minimum answer is L plus P minus 1, but if we want to use a power of 2 transform, which is what the problem most likely will revolve around, you would have to take that up to what? In this case, you'd go from 11 to 16, right? Because that would be a power of 2, and so on and so forth. And you actually are dealing with that in the project 2 as well. I have an FFT, an NFFT2 factor that you use to zero pad and make sure that the circular convolution done in the transform domain doesn't have time domain aliasing, and it's obeying that property. That was kind of built into that whole concept. So I'll come back to another example of this. In the notes, though, I put the multiplication theorem, which is just the dual of the convolution theorem where you're multiplying in the time domain and then circularly convolving in the frequency domain. And then there's also Parseval's theorem, which is out there. And then some other properties that we've been talking about. They're all kind of right in here, the same area. And I don't remember whether the DFT properties are on the cheat sheet or not. They are? Okay, so you already have them copied. You don't need to make a copy to bring with you. So we're going to look at some system implementation. I'm going to go back to another example that I put in here that I still haven't gotten to in the notes, but let me look at it in the notes so I don't have to get wrapped around. What's that? They're not? Okay, so make a copy to have them with you in case you need them, or you'll look at it in the book. And John will have his paper copy here. He's promised us to have it, right? Of my notes, not the book.
Oh, of these notes?
Yeah.
Yeah, I'll have most of them.
Okay.
Not all of them.
Okay, you didn't make the last 2 chapters, maybe?
I forgot, but,
No, you don't need them. You don't need them, so just this chapter you need now.
okay,
Also, I placed the review sheet on your spaces during the break. We'll be going through that at the end. It's been on the website, been on Slack, but I want you to be able to write stuff on there. And then I'm going to mark up mine while we're talking, and then I will repost an annotated version of the cheat sheet, or of the study sheet, so you know what we agreed upon during our review. So this example, I take a sequence that starts at 0 and goes up to 9, so it's 10 points. I take a sequence that starts at 6 and goes up to 13, but what we're allowed to do with our same theorem is the result of convolving these two together requires us having the length of the 2 sequences added minus 1. So the first case I take into account is 16, and then I say that for this particular problem we need actually to go up to greater than or equal to 23, because we go from 0 to 9, which is 10 points, and we're allowing space on the time axis for this thing that doesn't initially turn on, but it goes up to 13, so it's a 14-point sequence. So we have 10 plus 14 minus 1 is 23. Does everybody follow that? That's the rule. That's the length within the base that we're working in. You could probably get by with less, but then you would have to do some shifting around, literally, because you could shift this sequence over for the purposes of doing the circular convolution, but then you'd have to take into account the shift after you did the convolution to get it all right. And that, I'm holding my head because it's like, no, that was not the idea here. We want to make it more seamless than that. So just to prove that out, I did put that live in here. So I create the first sequence as A1, the second sequence is A2, and here I'm going to do the circular convolution with only a 16-point transform. And we see because of the sequences not starting both at 0 that we get a delayed output, but it's still going to be a trapezoidal kind of a shape, because that's what happens when you convolve a rectangle with itself, right? You get a trapezoid. But we're seeing it not decay to 0 on the left side or on the right side, because we haven't provided enough 0 padding. The top one is the theoretical linear convolution result. So taking this up, I'm going to take it up to 22 just for the fun of it. So we're going to be 1 point shy. It's looking very good, but we have one little point that wrapped around and time alias into the axes. So taking it up to 23 will clear everything up, and we'll be good on our base of 0 to 21 or whatever. So we actually end right here. Now it's clean. But again, if we were doing a transform, probably what we'd end up doing, if we wanted to use power of 2 transforms, we'd probably just say we're going to go with the next higher power of 2. And now we're going to go 0 to 31, so it would stop right here, because that would be 32 points, right? See what I'm doing? I'm saying we're going to do power of 2, so we start at 0, we'll go up to 31, and that will be 0.32. So this whole length will be how we achieved our convolution using the transform domain approach. I don't know if this is a good topic for the last day of class, but it's the way I organize the class, and I think it's acceptable. I mean, I gave you a project that you're using it behind the scenes, and you don't have to think as much, but you know, you're taking my word for it that it is in there, and we're going to still look at that a little bit, because that's coming up next in here. Overlap and add transform domain filtering. That's kind of where we're going next. So I have more discussion in here. We just kind of went all the way through this. So the next thing, I just want to make sure I didn't skip something because I'm pretty sure, yeah. This is just a pictorial of how we're going to convolve the sequences. We're going to augment with zero padding. So that's what we're doing. We're zero padding X and H, and then we take the endpoint transforms, multiply pointwise, and then inverse transform. So this is what we've just been looking at, a systems implementation. But the next thing is going to be even more valuable. It's more along the lines of what you're doing with the radio project. You're taking a very, very long sequence, 500 megs long, right? It's got a lot of samples in it. And you're going to be able to stream that through with a finite impulse response filter. So the next step in understanding that is to go to this level here where X of n is possibly infinite in duration, and this would satisfy pretty much all our real applications, say in radio and audio processing. We'll use an FIR filter for sure because we can't have them both be infinite in duration. That would not work with our FFT idea, but if one of them is finite and the other one's infinite, we can do a piecewise solution. So the piecewise solution idea is like this. We have a finite h of n, and then we take our sequence here and we break it up into smaller pieces. So we make subsequences out of it. We make subsequences out of it, and then we do the convolution, which is shown here in the DFT-IFT domain, by zero padding h of n and each of these subsequences. And that's what this picture is showing here. We're going to take and zero pad each of the subsequences, as shown in this picture as an example, and then we're going to take each of those subsequences and convolve them with the FIR filter, which is also zero padded, and now we get the filtered subsequences, which now extend into the zero padding because of the wraparound, because of the fact that we did zero pad. We don't have any time domain aliasing though, and then we just now drop down, so we have overlap and add, and that's what I was telling you about last week. This is the overlap and add concept. Is it cool or what? It's just it's a nice innovation. It's been around for decades and decades now, but back in the day it was a great discovery. So overlap and add. So we'll look at this one last example, and then we'll get into the FFT itself. So here I'm using two functions which I have in the SS module from when I first wrote it for the Dummies book. The Dummies book doesn't do anything with FFTs, by the way, but I just wanted to write it to have it in there. I was thinking out of the box at the time. I never thought I'd have a package that I'd publish, but it was inside of there, kind of undiscovered until I decided to put it in these notes. So it's called OA filter, which is overlap and add transform, and then the OS is called overlap and save. I don't think this will, overlap and save. Well, it says the same things. They don't have it's not uncommented. So here on what I'll take for my sequence, I'm going to take a cosine sequence of 60 samples. I'm going to take a simple moving average filter of 5 samples for the impulse response. So how am I going to set this up? I'm going to set it up with, I guess it sets it up automatically, I'm thinking. I need to have at least, I think, 10 points in the transform. I think I'm using more. So how do I define this in here? FFT size is greater than P, and that's the impulse response of the filter. but typically it's going to be a power of 2. So I'm going to make it be, in this case, I didn't make it a power of 2, I let it be 20. And then this operation here just lets it produce this extra matrix that comes out, so I can see, for the purposes of the demo here, what that's all about, to gain understanding of how the algorithm works. So run it through there, and then plot it, and let's see. Where did it go? Oh, I didn't plot it yet, I guess. I thought I did. No, I didn't run this. That's the problem. It was an old waveform for X. Okay. This brings up a good point that I hope you've all discovered by now in the class. That is the Jupyter Notebook. If you start writing in it and say X is something way up here, and then you eventually come down and move along and you decide to use X over again, what problems do you have? You might possibly start your notebook up again, or you end up having bad data. Remember, I told you that Pluto keeps you from having that error because it doesn't let you reuse a variable. But it's good and bad with it. Some people like it, some people don't like it. I just know that refreshing becomes the thing that you have to do. So, at any rate, this looks like the output of a moving average filter to me because it quickly gets into steady state, and it was a 5-tap FIR moving average, so that was the transient, and then from thence on, after it got in far enough, then it was in steady state. So what we don't know is that actually the overlap and add is running in the background. So I have a matrix inside of here which keeps all of the individual contributions from the subsequences in the rows of this Y mat. So it's got 4 rows, 60 points each. So we can plot those out individually, and that's what I did here. So that's just the decomposition using the input, which has been broken up into subsequences of length 20 and 3 times 20, or is it 4? 4 overlapping subsequences. I set 20. Oh, it's because it's overlap and add, so it's stepping half the length each time, just like in the project. But these are the overlap amounts. And then you have to add the overlap sequences together, and then it fits it together to create what we were seeing. This was in my notes, so I could go drill on it some more, but I'm not going to take the time on it. I'll let you do that. It's in the sample notebook, though. So that's pretty much the end of any Python demo that I had planned for tonight. So now we're going to spend some time on computation. So the FFT is an efficient algorithm for computing the DFT. What's so awful about the DFT? It's a beautiful algorithm, and for short lengths, it's not that big of a deal, and it's also very understandable. It's this equation right here at the top of the page. But in thinking about the complexity, we have to really drill into it and say, what are we doing? We're doing n points, and we're doing n components in each one of those endpoints. So we have, if we get down to the nitty-gritty of it, we have n complex multiplies and n minus 1 complex additions per point. So we have, in order to run that out for n points, we have n squared multiplies that are complex multiplies in worst case scenario, and n times n minus 1 complex additions. And the complex multiply, again, something that could possibly show up on the exam, and I'll be working my way through the review sheet here in a little bit, is this idea right here. We have x, which could be complex, and in the case of Project 2, it is complex, because remember, the waveform that's coming in, if you haven't looked at it, is a complex baseband radio waveform. So this definitely applies to the radio application. And we multiply times the weight factor, W sub n to the Kn. It's going to blow up into 4 real multiplies and 2 additions to manage this in the math. Python handily manages all of this for us. And if you were writing in C++, let's say, you can define a complex variable, a complex array, a complex vector as it's called, and you can do all the neat, transparent, complex variable operations. So really, we've grown up well. I mean, if you're doing it in FPGA, you have to have registers to hold the real imaginary parts, but we're doing all those things in our hardware implementations. It's just that we need to keep track of it because it takes up space and it also takes up clock cycles. So we're going to look at decimation in time FFT algorithm. And this, I'm pretty sure the history of this, it was the decimation in frequency that was first discovered, but the decimation in time is the one most books talk about first. So what is the history behind this? My understanding is it was a guy by the name of Schuster, which was studying sunspot periodicities. He was an astronomer of some sort, and he was looking at sunspots, and he was doing some processing of his data, and because it is periodic with the moon's cycles and our rotation around the sun, so something entered his calculation, and I'll have to say I'd have to go back and dig out the paper to read about it, but he developed some theory and some means of wanting to calculate some properties of that, and that's when he developed the radix 2 algorithm, sort of by accident. I mean, wanted to be more efficient. And I think to him, it wasn't that he was using a computer because they didn't exist in 1890 or whatever it was. He was doing it on paper, and he just wanted a more efficient way of doing his calculations for his research. Sounds intriguing. Look it up, and if you can remember the name Schuster, see if you find his name attached to it somehow or another. I'm pretty sure it's on the Wikipedia. I would diverge on that, but I'm not on the internet. Probably it's safe that way. I won't waste time, but it could be intriguing. But it was developed at IBM Research Labs then in '63, and I think there were actually 2 people, Cooley and Tukey, and they were at 2 different labs. I'm pretty sure if I may have that confused. One was at IBM, the other was somewhere else. But they were both in labs, and then they published, and then they realized they were both doing the same thing. So they both get credit, the Cooley, Tukey, radix 2, FFT. But then later they discovered this guy Schuster, you know, a long time further back. He gets the bigger credit, perhaps, but I don't know how that works. These things happen throughout history, though, right? Inventors and inventions are later found further back in time. So what's the big deal about the radix 2 decimation in time? First off, we assume we're going to use a power of 2. So we're going to always add a power of 2. 2 to the nu is the way the notation works here. Nu is some integer. So why did they do this? This I don't know. This gives you an idea if you're going to be an inventor of something great and wonderful, how are you going to come stumbling into it? Who knows? I mean, right? You don't know what leads your mind one way or another because we don't always think linearly. We sometimes think in some bizarre way where we don't even know why did I think to do that, or maybe even make a mistake, and then that leads you to discovering something. So for whatever the reason was when they were looking at this, they were just questioning, I'm guessing, can we do something with even and odd? So we're going to have a power of 2, and we can do it repeatedly if we're doing things with a power of 2. Like if we start with 16, we can go to 8 and 8, and then we can go to 4, 4, 4, 4, and then we can go 2, 2, 2, 2, you know, 2 times 8 would be 16. So that's the way this algorithm gets developed. So it starts by saying, let's break it into even and odd points. So they take the points in the DFT algorithm, they say, let's do a sum over the even contribution and the odd contribution. And then they say, let's re-index to step or to stride in factors of 2 over the data. So they put 2r into the even and 2r plus 1 into the odd. And then the next thing they do is they say, oh, on the odd, we have this 2r plus 1, and in our twiddle factor, w sub n, we have a w sub n to the 1k. Well, that's not a function of our sum index. We'll pull that out in front. That seems fairly benign, but that ends up being an important factor onto itself, just the basic math of it, how you would simplify it down. So the next step is to notice that w sub n squared, which shows up inside of here, is actually, if you go through the expansion of what it is, it's just w sub n over 2. So we're dropping the basis of how the DFT of those even and odd points is calculated. We're not using a basis of n points anymore. We're using n over 2 points basis, which is another really key factor as well. So when you take that into account and rewrite it the next time, you have the w sub n over 2, and then what you have is you have this factor sits out in front, so you have two n over 2 point transforms being calculated using a base of n over 2, which is appropriate for the even or the odd points, kind of thinking abstractly. And then you bring those two n over 2 point DFTs together with this weight factor w sub n to the k. So this ends up being the only factor that is related to the original length n. It doesn't seem important right now, but it is. It's actually also very important to recognize that fact. So what the block diagram looks like is we have two over n over 2 point transforms. We've broken it up into the even points, the odd points, and then we combine the outputs of those together, which I like to refer to as combining algebra. So we have bringing a point across, and then the diagonal point comes in with a w sub n to the k, and that's going to make things unique with respect to the n points that we were setting out to do. So if you sit back and look at this one step of the radix 2 algorithm, we have 2 times n over 2 quantity squared for the n over 2 DFTs. That was the matrix calculation, right? It was n over 2 squared, like a matrix times itself. And then we have the combining algebra has n complex multiplies down that final column there to combine the points together. So that's the number of complex multiplies. Complex adds, similar. The important kicker, though, here is that what are we doing in multiplies? We're having n multiplications plus n squared over 2, and this is the big savings here. This is where things start to get better. If we look at that, even for one decimation, we're looking at n plus n squared over 2 as being less than n squared for n is equal to n greater than 2, and that will only get better. This seems really modest and really meager, and might be the thing where you'd get discouraged after scribbling around, or I'll just use U-Lake as an example of somebody got fascinated with types and just kept drilling on it, right? So you could have been the more average person who would get bored immediately and walk away, just like a freshman engineering student would get bored and say, I don't want to do this, I'm going to walk away. So you know that was true, right? When you were a freshman, there were people that you know dropped out.
They dropped out because they can't keep up.
Yeah. So just like anything, you know, you have to stay with something and you have to give it time. So the next thing is to do this again. So now, because of the fact that we have, and I'm going to try to make this go faster, because of the fact we have n over 2's here, we can take each one of those n over 2's and break that into 2n over 4's, and then 2 over n over 4's at the bottom, and then do combining algebra on that, and then just keep backing up to the left with until we get down to the two-point transform is what we're going to do. And I'm just going to sort of cut to the chase here of saying that there's the 2n over 4s, and then finally we've done it one last time on an 8-point transform. We're going to have 3 stages or 3 passes across the data. So we've kind of tangled things up here. It's called bit reversing, but we have these 2-point transforms which actually form the combining algebra. So we have fundamental to the FFT, it's called a radix 2 butterfly. So there's one right there, and then I can identify it deep inside. So there's the radix 2 butterfly is the basic computational unit, which is spread throughout the radix 2 algorithm. And if you go with the radix 4 FFT, you have a 4-point transform is the fundamental unit, and it's a little bit more efficient multiply-wise than the radix 2, but it's the same idea. So here's our signal flow graph that we've seen in the filtering chapter. If we use our theory of transpose, remember the flow graph transposition theorem, we could reverse this algorithm and run everything backwards. So we'd start at the left-hand side there and drive it in the opposite direction and reverse all the arrows, and we reverse the input for the output. So that would be the radix, or the decimation and frequency algorithm. That's just the dual to the decimation and time algorithm. So to get this all distilled down, we make this revelation that if we put all the passes together, we have log 2 base passes. Just to refresh your memory, this is the rate. This is an 8-point transform, so we have log 2 of 8 is 3. So we have 1, 2, 3 passes through the data. The data loads in, and then we can set up the algorithm, and this is what's called an in-place algorithm. So these 2 points go across here, and they get replaced by 2 new points calculated here. That's called in place, memory-wise. And then when we go to this last pass, we have the butterfly there, which would be done in place as well in data. That's another efficiency-saving thing that was recognized in all this discovery. There's a few more little tweaks, but if we just go to that point, we've got n passes, or log base 2 n passes, and at each pass we have n complex multiplies. So that's the core efficiency of the radix 2 algorithm, and this is just an example. Direct evaluation on a 10-point transform would be over 1 million complex multiplies. That would be the n squared value there. And if you do it with the radix 2 FFT, we're over 2 orders of magnitude more efficient. Does that, as an engineer, we should be excited about that, like very excited. It's like riding your bicycle up a hill or something, which, I enjoy the exercise of all that, but if you could crank less cranks, you would you'd be a lot happier, probably. Not your body, because you're supposed to be exercising for your health, right? But whatever. So another thing we can do to even save more is we can look at working with the butterfly and simplifying. We can simplify the butterfly. Half of the points just involve a sign change. So we can take our butterfly, which has these 2 branches coming into this node, or the nodes here, the w sub n to the r and w sub n to the r plus n over 2, and we could recognize the fact that this is the same as minus w sub n to the r, which is used in the upper branch. So you can just pull due to linearity, right? Linearity will pull this w sub n out of here and here, pull it out to the front side, and then we just have to put a minus sign in there. So we save 1 multiply. So we finally get down to the value that I want you to memorize, which is in the cheat, or the crib sheet we're going to go through, review sheet. That is the basic number of multiplies. That's the basic efficiency rule or formula for the radix 2 FFT. Good? It's simple stuff in the end, but it's just getting there and kind of justifying it. I've already talked about in-place calculations. That's a big deal. Bit reversing is literally bit reversing indices, so just pull a value out in the middle here, like x3 would have, for 6, in terms of bits turned on, we turn on 4 and 2, and then if we reverse those bits, flip them to the opposite side, that would be 1, 1, and that's a binary 3, so that's how bit reversing can be done in code or in register arithmetic to manage that reversing operation. Here's just a table using the numbers we've come up with. And of course, this improvement factor gets bigger and bigger. I was having you in the midterm or the exam I just graded using 2 to the 13th, right? You're using an FFT inside of that spectral estimator for that problem with the quantization noise. And this is an ANSI-C FFT, which I've converted to a class in C++. It's not super efficient, but it's something that I've played with a bunch. Just an FFT algorithm, just to give you an idea, and it's got different stages to it. There's the bit reversing part of the algorithm, and then there's the butterflies, and then there's the creation of the table. In this case, the table is filled initially, but you could start off with the twiddle factors stored in memory. But in this case, the table gets created on the fly as the algorithm starts up. Something for another time. So decimation and frequency, I've already talked about it. So here's the development of it, and then here's the final picture. So this looks like what we just went through, just network transposition happened there. Then in terms of computing the IDFT, we have to take into account the factor of n and then the conjugate. So the simplification there, it was also in that C code. You can make this a separate stage where you do the shifting, and if it's powers of 2, it could be done with bit shifting. And the conjugates is just flipping things in registers. It's sign changing. It's not multiplication, actually. So they're on the same order of magnitude to do the DFT and IDFT. So the rest of this chapter, before it goes into spectral estimation theory, which I don't think I'm going to spend much time on, but I'm going to look at it briefly, are some cool applications of the FFT. So one kind of neat thing is 2 real endpoint sequences using an endpoint FFT. So you can take an endpoint FFT and FFT 2 endpoint real sequences at the same time. That's sort of like tricks of the FFT workers. And that's talked about here. Another trick is to do a 2 endpoint FFT using a single endpoint FFT, and then you just have to do some combining at the end of that to get your 2 endpoint FFT, and that's done over here in 2 steps of extra math, which do add on some more calculations, but I believe they are less, it's more efficient than doing the radix 2 on the double length transform. And then there's going back to what we've already talked about. Here's the picture that I put in the notes from last week for the project 2, overlap and add, or overlap and save, and then overlap and add is talked about down here. This was not talked about earlier, but it's in the SIG-SYS module, and this is just the variation on doing transform domain filtering. A lot of this stuff is interesting, but because you're getting exposed to it in project number 2, or those of you that have finished, you did it and it worked, right? You got to listen to signals that were kind of noisy and maybe other signals in the background, but if you were gathering intelligence, I think you still got the point. I mean, talk radio is talk radio. So the sports stuff makes sense. Some of the other talk radio stuff can be all over the map if you're listening to talk radio. If you love that stuff, you can get hooked on it, because I think people are. I have their favorite talk radio host, and they just tune into them. I find it interesting, but not so interesting that I want to spend any time on it, because the internet's full of all kinds of stuff that's not necessarily good for your health either. Okay, so the next and last thing I want to just briefly go over is Fourier analysis, developing a spectrum analyzer using the FFT, and that's what our oscilloscopes do these days. And this is just some fundamentals of spectrum analysis. This is the two main things that I look to the FFT for are transform domain filtering, which we've been talking about, and building a spectrum analyzer to spectrally analyze a record of data, or doing an ongoing spectral analysis. Like, I'm thinking of people that have seismometers running around the world, and they're looking for countries that are testing their nuclear weapons, and they're looking for signature events that they would see if they're constantly looking at their seismographs. And of course, you know, tsunamis and other things that happen, that you could detect periodicities or other things where spectrum analysis would be important. And where else I use spectrum analysis in radio stuff and radio signals, but mechanical engineers use it a lot. You're going to look for vibrations and other things in a mechanical system, and spectrum analysis is important there. So here's our front end, anti-aliasing, continues to discrete. Now is when we're going to want to consider the windowing aspect of it. We have windows that are used in filter design, but then windows used in spectral analysis, which I introduced way back when at the end of chapter 2. Remember, we truncated a short cosine sequence and then put a window on it to get better enhancement of the spectral lines. So this is just going through the phenomena that goes on with the anti-aliasing filter, and then getting at the spectrum of your signal. This XC is, from our block diagram, is the original analog signal, but then we have the phenomena of the window function. So the window function is brought in here as the convolution, because it's going to be multiplication in the time domain, so we're convolving the window function with the spectrum, and that's going to create a blurring effect on the spectrum, and that's what this is showing you, the blurring that happens when the shape of the window and the frequency domain circularly convolves with the spectrum. Okay, this is going to be on the review sheet, so I'm just going to briefly look at it, but we're going to come back to it. If you're building a spectrum analyzer, very simple rules on how to design the spectrum analyzer. The two basic properties are, if you want to cover so many hertz or megahertz or whatever, a frequency spectrum, what are you looking for? You're looking for the resolution, and you're looking for the range that you want to accomplish with a number of DFT points. So we have the DFT points will directly relate to a particular point on the analog spectrum analysis. If you're thinking in sampling theory, and that's what this is, we have FS, we have the DFT point K, we have the DFT or FFT length, so we can get the frequency in hertz of a particular DFT point, and then we can get the spacing between the two points side by side, very simply, is just Fs divided by n. So that's a really important design parameter. If I want to have sub-hertz resolution and I'm sampling at a megahertz, I've got to go to a power of 2 that gets me, you know, from megahertz down to less than a hertz, which is going to be some FFT length greater than 1,000,000 to go from megahertz down to sub-hertz. Some examples here that are in the book talks about windowing and sinusoids that are close to each other and the resolvability, and this is what we were first looking at way back in chapter 2. And if you bring them closer and closer together, eventually they blur together, so you have a resolution limit, and then you can improve things by putting in a window function, and you can get the side lobes to drop off faster, which reduces the spectral leakage. So that's what's happening here. Each of these spectral lines is producing leakage, which is blurring things together when they get too close. So you can improve that with the window. And so there's a discussion of windows in here. Hamming, Hanning, Blackman, and Bartlett. I fixed the notes up last night or this morning. I just said Han is in my notes, or Hanning, but the guy that invented the Hanning window is Han, and I think it was just crude terminology amongst DSP people to say it's Hanning's window. You know, the guy named Hanning, just like when I went to school at Michigan Tech, a lot of my classmates were from Detroit area, and they would say, I work for Ford's. Do you know anybody that talks that way? They put a possessive thing on a name. I work for Ford's, I work for Chrysler's or something like that. I mean, I think that's where the term Hanning came into vogue. They just said it was Hanning's window, and the guy named Han, and we talk about him as Hanning. I don't know. That's just my guess. I think he's Scandinavian, so I'm not sure that even factored in. Maybe it was an English translation thing. But at any rate, there's his window, Blackman, Kaiser Bessel, which is a variable type of window. So the bottom line is when you put all this stuff together, you get the different window shapes, and if you're going to do a spectral analysis, you look at the trade-offs between the windows. The rectangle is the narrowest main lobe, but it only rolls off. It has the highest side lobe at 13 dB, which is really poor. It only rolls off at 6 dB per octave, where the Hanning has the fatter, or the Han has the double wide window, but it rolls off at 18 dB per decade, which is very, very nice. It drops away, keeps the leakage down a lot. And then we have variable windows like Kaiser where you can adjust what you want to get from it. Other properties is if you're not commensurate, you end up with the frequency that you're looking at is not at one of your FFT bins, so it actually can get degraded. It's called a scalloping loss because it will fall in between two different FFT bins and it will drop down a little bit. The only way to fix that is to maybe change the window shape or just fundamentally use more points in the FFT to get that resolved. So what else do I have in here? I think I look at resolving leakage, and this is the case where the hand window allows you, even though you get less resolution because of the wider main lobe, you can pull something out at a lower dB level because of the 18 dB per decade or octave roll-off versus the 6 of the rectangular window. So this might be, say it's a mechanical application where this is some vibration in a bearing or something, or shot bearing. You know, I don't really know. I don't go into the tire store when I buy my tires from Discount Tire, which is where I usually get them here in Colorado Springs. They balance tires. There are a lot of applications where FFTs would be involved in mechanic stuff. I mean, I think most of us might be driving, if you drive on a tire that's out of balance, you're going to notice a small amount of shimmying, right? If it gets worse and worse, then it's dangerously bad. If it's very tiny, it would probably be something way down there that they could identify for a bearing issue. For me, it's intermod or something like that. Like you also hear in the project, you hear two signals on top of each other, one of them which doesn't belong there. I won't say anything more because those of you that haven't done it, the project yet, need to play with that. That's all I have in what are the other chapters? I have a whole chapter that focuses on advanced stuff, like average periodogram is what we're using in exam 2 for the noise spectra. And I'm just going to go take a quick look at that so you can get an understanding of at least what goes on with the average periodogram. It's a way of handling random signals, and the basic idea with the average periodogram is you take the record of data, which is x of k, and you create some non-overlapping or possibly overlapping segments. In the one I was using, where I get to set the noise mode or the sinusoid mode, the default overlap is 50%. Because you're using a window, you can get more mileage out of your data. If you don't use a window and you try to overlap the data too much, you're going to get bias built in because you're going to have data reused, and it's going to be like corrupting your own. But if you're tapering it down at the edges, then the overlap is acceptable, and you can keep the resolution up by having each segment have more points in it, which gives us more resolution. And then you average the segments to average out the noise, because the periodogram basic property is more frequency domain points does not effectively average out the noise. It's counterintuitive to think that you could get more data and you would get rid of the noise, and you would not get rid of the noise, but that is in fact the case with the periodogram. You have to average it. That's talked about in this chapter. The chapter that I'm not going to look at all was in the olden days when I used to teach this as an undergraduate class. We would spend time on digital filter design, and we didn't have the tools like the MATLAB filter design toolbox and so on and so forth. So we had all the math of working with Chebyshev and Butterworth and elliptic polynomials, and just going from the S domain maybe to the Z domain with the polynomials, which I know you see some of that in circuits classes, Butterworth and Chebyshev and so on. So this just is historical. It does pop up in, when I used to teach real-time DSP, a little bit of this, but still nowadays, in the beginning I thought relying on filter design toolbox was cheating, and it was not the right thing to do. You had to do it the hard way from scratch, but now it's the normal way of doing it. So I'm over with that for sure. So now we get to the final part of today's lecture, and that is the review topics. So, and I want you to ask me questions. This will answer for everybody if there's something that you're not sure of. I have not looked at old exams, so I don't know what I'm going to pick, but I am going to look at this sheet and I'm going to say, I said this, I'm going to do it. And if I don't do something and I think I'm going to do it, it'll just be good for you because you won't get tested on something that maybe you weren't prepared to do. I'm not intending to do that, but first off, it's comprehensive, but new material that you haven't been tested on, which is the last two chapters we've gone through, the structures and the DFT, FFT, those are emphasized. So that's a given. About 5 pages as possible. I'd make it 6 if I want to break it up more. Final exam time slot, I believe, is just 2 hours. Is that correct?
Yes.
When I first started teaching, it was not. It was longer. It was like the night that we met. That's how much time you'd get. Open book, open notes. I'm going to bring my book. I probably won't try to ride my bike next week. I don't know. Maybe it'll be snowing out and I won't want to kill myself on my bike. But I'll bring a book. Anybody that, that doesn't have one, because you can't use an electronic version of the book, will have at least a couple of them here. And John has offered up his notes to share. He'll have priority on them, though. I think you can assert without fisticuffs or something how you're going to make sure you get the notes when you need them. If you want to burn the paper,
If I printed it in the library, it'd be like $20 anyway.
yeah, you can do it. I mean, you can do that if you want to.
Yeah.
So, part 1, part 2, everybody good on that? And I'm going to contemplate, based on your input, whether or not we might want to start at 4:45, 4:30, or anything. Just give me some ideas, and then I can bounce them back in our, or you can put them in, not to me, you can put them in the Modern DSP chat, and everybody else will see it, and you can settle on stuff. Remember, at the beginning of the semester, I emailed everybody, and you guys started responding to me, and that helped me figure out ideas on class time very rapidly. And you understand that we didn't get to this point by not having some interaction going on, and we were easily successful because of only 4 people. I don't get paid very much for teaching this class, and I'm kind of discouraged to do as much work as I do, and I'm also thinking the university didn't make any money at this either. I think we have a problem financially. I don't know how this can be sustainable, but
Like this class you're talking about?
yeah. I mean, if all your classes only had 4 people in them, how would we even have the lights to power the building and all this other stuff? So you can't be complaining about what you got, I don't think, because it ran. And if this was interesting and exciting, I'm glad that you had the opportunity to learn about it, but I don't know what's going to happen. I'm actually a little bit worried that jobs aren't really going crazy right now, and I was supposed to advertise that there's a job fair in February, and you guys can come back to any job fair you want to. If you're working and then you think maybe you don't like your job already or whatever, you can always come back to a career fair. So I think it's February 13th or something like that. I'm not on the internet, so I can't log in, but if you want me to send you the link, or just I don't know who's going to keep you informed once you graduate to know when these fairs take place, but you're always welcome to come back and use the network of UCCS to help you get a job, because right now they're crazy. They're really asking for people that haven't enrolled yet for the spring. They're trying to give you an incentive. Did you see that email today?
For what?
Well, it's just to get undergraduates to register for spring classes. They're offering, through a lottery, a free parking pass and some other food perks and other things like that.
Okay.
They're just...
We're getting out of here just in time.
I don't know. I've never seen anything like that before.
Yeah, that's weird.
Free parking passes, that...
I wonder if the enrollment's gone, like, the total enrollment has gone down. Like for freshmen?
I don't know the answers.
I've heard of the freshman class has, like, gone down big time.
Yeah, let's keep going on this because we're going to be late and getting out of here. Okay, so relevant topics. We started off with the first bullet there, discrete time signals and systems, basic signal types, LTI systems, convolution, sum. I'm committing to something from this area is likely. It might be as basic as, if I gave you a circular convolution problem, I'd say do also the linear convolution, and that would fit into this category. Classical solution to LCCDEs. That was one of my fun things, like types. I wanted to learn more about classical solutions. I know most of you weren't fond of it. It's not on the exam. It's definitely a no. DTFT and LTI systems, signals and spectrum, theorems, transform pairs, something, I can work something on that into a problem very easily, and it's very likely that I will. I can't say how big of a thing it would be, but something. Z-transform, I like that topic. I think it's something you guys like. There will definitely be something on that. That's what I consider to be bread and butter from the class. Low-pass sampling theory and aliasing, not any dragged out problems like you did either in the homework or in exam 2, now I might say in the spectrum analyzer thing at the bottom, you at least have to know Nyquist sampling theory. You know, if I tell you the bandwidth of the signal goes to 500 hertz, you know you need to sample at least 1 kilohertz. And if you want to get a certain resolution, you're going to divide that number by some n, and then you're going to raise it up to get a power of 2, and then to get your frequency resolution. That's at the very bottom of the page here. So that's as much sampling theory that I would like you to know about. If I gave you a short answer question, it said, in digital or in communications theory, can we ever violate the sampling theorem by undersampling? And your answer would be yes, but the details of it would be, I just know that we saw that in class with one set of examples. So it's something closely related to twice the bandwidth of the signal. That was what you'd remember. You'd say, as long as I'm somewhat greater than twice the bandwidth, I might be able to make it work if I'm careful with it. Okay, D to A to D. Maybe a comment about quantization noise. It wouldn't be that simple formula that relates to what is signal to quantization noise ratio in terms of signal power and the number of bits. But I don't have it in red, so it's not very likely. I put things in red last night that I noticed. Transform analysis. This just gets involved with picking whether you use time domain, frequency domain, or Z domain. So I just say as needed. That just has to be at your discretion, how you think you're going to do it. Magnitude, phase, group delay, that you know they exist, but without tools running on a computer, you just know of them. So I can certainly ask about linear phase filters as being constant group delay, and you know that already, and maybe you do a calculation or something to just verify that. But you know the midpoint of a FIR linear phase filter would be the group delay, the midpoint of the filter. All pass systems, one problem for sure on that. It will either be minimum phase with all pass or minimum phase with linear phase. And I guess I'll just say it might not be all pass, it might be linear phase, because I gave you an all pass on the exam too, possibly, even though I don't say that in here. Do you want me to nail that down? I'm willing to say right now that it's more likely going to be linear phase and not a repeat of the all pass that you just did. Is that? The reason why I'm putting that in here is because my words are one problem in this area for sure. I'm pretty much already committed to saying there will be a problem, and now I'm committing to just saying it's going to be a linear phase as opposed to all pass and minimum phase. Structures, yes, definitely something with structures. And basically, it'll take one of two forms. It will either be I give you the block diagram and you tell me what the system function is in the Z domain, or I give you a system function h of z and I say create a block diagram or flow diagram, flow graph of, a direct form 1 or 2, transpose, etc., cascade type of thing. It will be something not that intense. It'll be very simple, but you have to make sure you keep the types straight. Not anything on FIR though. Finite precision, what did I say here? It would only be a concept type question. And I'll be honest with you, I very rarely, if ever, put short answer questions on final exams. It's generally work something out type problem. So I'm very doubtful that I would probably do that, because I'd rather just have you calculate something. I mean, what would you rather work out an answer or have soft thoughts to write down? Most engineers like the hard stuff, the hard writing out an answer rather than something soft. Okay, then we're moving down into DFT, which you just talked about. So basic spectral analysis and circular shift, circular convolution. So there'll be something in that area for sure. And it's going to take the form for the spectral analysis based on, it could be a block diagram, it could be something where I say you're going to build a spectrum analyzer and you're going to have to pick, say, the FFT length, and you're going to have to bring it up to a power of 2, and you're going to have to discern what the proper sampling rate is, like low-pass sampling theorem. And then maybe I could add on to that to say, draw me a block diagram of how this system will be set up, and then how many complex multipliers will be involved with computing that spectrum. That would be the n over 2 log base 2 calculation. Or questions might be things like the DFT point, if this was like 2048 DFT points out here, what is index 984, what frequency does that correspond to? And that's this simple formula right here. I think it's on here. I thought I put it in here. Now I don't see it. This was in the notes, though, just a second ago. And this pencil's not working good, because I guess my video's too long. It's K times Fs over 2. Over N. So if we were at 0.992, let's say, once you design your system, and you had picked your sampling frequency and you knew what N was going to be, and it's going to be a power of 2, because it'll be more efficient, then you would plug that K value of 992 in here, and then Fk would be the frequency that it's at. That's, if you look at your FFT spectral plot, that would be the frequency that you're at. Oh, never mind, it's right here. I knew it was in here. Point K1 corresponds to K1 times Fs over N. So it's right in there. And the thing that I did in this plot down below here that I think holds true since chapter 2 is we know that omega was always related to Fs in hertz, and then we had Fs in normalized frequency, which is omega over 2 pi. And now what we've added, and is another axis in the DFT domain, is the integer DFT points. So if I construct a figure or a drawing where you have to pick something off because you're seeing this, and then you know it's related to the F in hertz or in radians per sample, you know how to relate all that stuff together. And at this point, we are out of time, quite a bit actually, about 7 minutes. What I suggest, though, is you're going to write to me on the Modern DSP channel what you think about taking the exam in the lab upstairs, which is right next to the lounge, and the bathroom's around the corner. So it's not as beautiful a classroom as this. We can do that. So you can talk about that on the Modern DSP Slack channel, group channel, and if there's questions about this cheat sheet or something, you can also bounce things around, not keep it in secret unless it's something you want to be in secret. You know, like if you think it's the benefit of all of us, let's just conjecture on it, you know. One of you says, you said this, it's not clear to me, and then you write it out there on the Modern DSP channel, and somebody else says, no, he said that, this is what I got. And then we'll all see it, and then I'll chime in and say, yeah, this is Yeah, this is what I meant, so. Are you bringing your hardware back to Toronto? Or you,
He told me to drop it off at the ECE office,
okay,
but I went twice today, and they were closed both times, so I'll go
okay.
tomorrow.
I'm gonna stop the video before my computer dies here.